Hi everyone, this is Miss B again. Again, I hope everybody is healthy and doing the best that you can during this situation. So what I'm posting now is the continuation of energy. This should be the last concept that you need to know for energy before we regroup and talk about our plans after this unit. So for those of you who have been following along in Schoology, I'm very proud of you. I know this is not easy to do on your own, but just remember if you have questions on any of the material, I do respond to email or to a Google chat, or if you have your documents in your folder, those should be Google Docs and I can comment and answer your questions. And some of you have done this already, so good job on that, and I hope I'm helping. So just remember, if you have questions during the normal school hours, 7:30 to 3:30, I will respond right away. If you ask me questions outside of those hours, I'll get back to you the next day, okay? So again, just do the best that you can to try and follow. And if you have questions, please ask. Now again, you do not have these notes with you. You do not have a physical copy, but I have posted the notes and these lectures in Schoology. And the videos are also on YouTube because I'm not sure how well your Chromebooks can open up the original file. So again, you don't have to print these. You can if you want to and fill it in. I'm just hoping that you try to follow along here and understand energy as best as you can. All right, so where we're going to pick up with this, the start of this will look familiar to you, but fair warning, there is math again at the end of this. It's another Q equation, but believe it or not, it is a little bit simpler than the original Q equation, and you will see why. All right, so what you're looking at is a nice diagram here that should look a little familiar to you, right? So I chose water. So on the left here you have ice, then you have liquid water, and then you have water vapor. So what I'm trying to show you are the different changes in state or phase changes for water. So that should sound familiar. We did talk about phase changes. But what you should notice now are that we have arrows going back and forth. So if you come by the ice image right here, so you have an ice to the arrow of liquid water, so that's a phase change, right? Solid to liquid is melting. And then if you reverse that, liquid to solid, that is called freezing. Now how about we go up to the vapor? So from liquid water to the vapor, that's boiling, right? Liquid to gas. And then if that gas reverses itself and goes back to liquid, that's condensation, which we did talk about. And then off on the left here are these funky phase changes. So if you have a solid to a vapor, that is called sublimation. And then vapor back down to a solid, this is called deposition. So these are very weird, funky stages. And what I will do is put a couple of videos up in Schoology so that you can take a look at this. I don't think you've ever seen this in your life. Maybe if you've dealt with dry ice, you've maybe seen this. I'm not so sure. But in any case, I will put videos up of iodine. So it's going to be a solid going to a gas, and then it's going to reverse itself, just so your eyes can take a look at what this is. Okay, but you should have heard of freezing, melting, boiling, and condensation. Okay, so if you just look at my questions now, either on the screen or if you just have the notes packet up. So I did post this in Schoology. You have this to just follow along with if you'd like. If not, just follow with the video. All right, so my question to you is, at what temperature does this ice freeze? So when did this liquid become an ice? At what temperature? Well, if you're here at Chicago, where it's the normal ATM, the normal atmospheric pressure, unlike Colorado, right, where it's a lower pressure, this would be 0 degrees for us in Celsius. Okay, I'm not Fahrenheit because for science we use Celsius. Okay, but then my next question is, at what temperature does that ice melt to become a liquid? So if you notice, these arrows are going back and forth, so the answer to that one is also 0 degrees. So this is what we call equilibrium. So the freezing point and melting point of water is the same. It's both 0 degrees. Okay, now what if we raise the temperature to evaporation, so up here? So this liquid water, at what temperature does that become a gas? But in your terms, maybe at what temperature does water boil? And for us in the lab, here in Chicago, normal ATM, that'd be 100 degrees. But what if it condenses? What if that vapor condenses back down to a liquid? At what temperature does that occur? And if you notice, the arrows are the same. So again, it's 100 degrees Celsius. So what I'm trying to show you is this idea of being in equilibrium, these states of matter. So at 0 degrees, ice can either freeze or melt. At 100 degrees, water can either vaporize or condense. So that's what we call equilibrium. Okay, so what you're supposed to notice is that, and this could be any substance, this doesn't have to be water. I chose water because I thought you'd be pretty familiar with it, but melting and freezing points are the same. Evaporation and condensation points are the same. So that's the topic that I'd like you to try and think about and focus on for this last lesson. Okay, all right, so for melting and freezing now. So what I'd like to show you is something that you're going to be dealing with. So it's kind of a new word for you, but the concept should not be too unfamiliar. So if a substance is going to melt, right? If it's a solid and it's going to turn to a liquid, whether this is butter or ice or whatever, it takes energy, right? Which should sound familiar from our previous lessons, or heat, right? Heat to do so. So there's a value needed for a substance to turn from a solid to a liquid, and it happens to have the term heat of fusion. So fusion indicates melting. Okay, now if you reverse that, if the liquid turns to a solid, if you're making ice cubes, right? So you have liquid water, put it in the freezer, and then later on it becomes ice. So that is called solidification. It becomes a solid. Now when this happens though, heat is actually lost because you feel it as something cold, right? So it takes energy for that liquid to turn to a solid. When it does so, heat is lost and we feel it as something cold. So that's just called heat of solidification. All right? So these two are actually equal to each other, right? That's why we had those arrows over here, right? So they're equal. So there's some energy involved in this, and that energy is going to be the same value. So it's either fusion or solidification. So just some new words that go with this. And then the same is true for vaporization and condensation, right? So vaporization is when a liquid becomes a gas, right? So if you boil water, you see that bubbling there, right? And then you feel the steam. That takes energy. It takes heat to change a liquid into a gas. And that's called heat of vaporization. And now the reverse, right? If you pull a can of soda out of the fridge, right? You see those water droplets on the can? That is a gas turning into a liquid. If you feel it as something cold, then that means the heat was lost. So that's heat of condensation. Okay, so these two at least keep their same names from their phases. Up here, the fusion was a little bit different for us. But in any case, it's vaporization and condensation. So they are equal to each other, just like you saw these arrows here. Okay, so this is the idea right now. All right, so why am I telling you about these heats? These are values that you are going to have to deal with, just like we dealt with specific heat in our previous lessons. So in this case now, these heats of vaporization, it's still joule, but it's going to be joule per gram. And if you remember from specific heat, that had all three units. It had joules, grams, degrees Celsius. These heats, when they're equal, right, vaporization, condensation, fusion, and solidification, if those temperatures are the same, then temperature is not part of our units. But I think the graph will be a little bit easier to see now. So what you're looking at, this is called a heating or a cooling curve. Okay, so it's a little bit easier than those phase diagrams that we were working with. So if you look on the left, you have temperature in Celsius, and on the bottom, you have heat being added. So that's why these lines are going up. This is called a heating curve. If you started at the top and worked your way down, that would be a cooling curve. Now, if you notice, the order of the phases does not change. Solid, liquid, gas, right? Same as the phase diagram. But what you should notice now are these straight lines. And these are the lines that we're focusing on. When I asked you to solve for Q in the previous lessons, that was these lines right here, these lines that were increasing because the temperature was changing. Now, if your phases are in equilibrium, there is no temperature change. That's why you have a straight line. Notice there's no T changing here. The line is straight. So if a solid goes to a liquid or vice versa, you can see the melting and freezing going back and forth. Up here, liquid's turning to a gas or gas to a liquid. condensation and vaporization are occurring at the same temperature. So these are the areas we're going to focus on these heating and cooling curves. These are called phase changes, and that's what you'll be calculating, the energy that it takes for these phases to change. Okay? All right. So this chart is just showing you the real values for these substances. This is nothing you need to memorize. You're going to use these the same way you use specific heat. These are set values. You can look them up. I just wanted to show you a few of them for some common substances. So here's water. So this is the heat it takes to melt or freeze it. This is the heat it takes to condense or vaporize it. And then here is ethanol, which is a type of alcohol. So you can see the numbers are a little bit lower because alcohol is more volatile, right? It doesn't have the same type of intermolecular forces as water, so these will change phases easier. Here's copper and lead. These are two metals, and you can check the difference. I'm not asking you to analyze this or to try and deal with this on your own. You just need to use these in the problems that I set up for you. So these are set values that I just wanted you to be aware of. Okay. Okay, so just take a look at this heating curve that I have for you here. This kind of summarizes the whole energy unit here. So we're talking about phase changes, right? So if a substance goes from a solid to a liquid or a liquid to a gas, it takes energy to do so. So why do I have two different Q equations? So this one right here with the M delta T Cp, that's what I taught you earlier. So why do we have specific heat in this delta T? That's because the line is increasing. So there is a temperature change, which is what delta T means. And the energy to do so is called Q. And then the Cp was the specific heat. So every substance has a different ability to raise the temperature of 1 gram of itself 1 degree. That's specific heat. Those were set values that you were supposed to use. Now here, this QpH is what I will show you in a separate lesson because that's the math. So right now, if you notice, that Q equation looks a little bit different. There's no delta T and there's no Cp. That's because the lines are straight and there's no temperature change involved. So this slide is a really good summary of what I want you to know for energy. Okay, so there's energy involved to change the state. And when there's temperature involved, you will use this Q equation. If there's no temperature involved, you will use this one. Okay. Okay, so what I'm going to finish up here with is a little introduction to that second Q equation, and then I will stop it and then just put up a separate video to help you along with the math. Okay, so what I'd like to show you first, though, is this example. So just take a look at this. So let's just read it together. It says, what is the heat transferred? Okay, heat is Q, when 20 grams of ice melts. So 20 grams is the mass, and then I give you the specific heat of water. So I'm hoping if you've been following along, this looks familiar. This is Cp, and you can tell by all the units. So joules, grams, degrees Celsius. And let's see if you notice anything here now when I try to solve this. So this is the Q equation that you know. This is what I originally taught you. So let's plug in what was provided in the problem. So you have 20 grams, which is up here. 4.18 is the Cp, which is right here. Now, why do I have this 0 to 0? Well, what did I tell you in my original slides, right? Ice melts or ice freezes at the same temperature. So it's 0 to 0, right? It's that straight line on the curve. It's this point right here. So that's 0 degrees. The temperature is not changing. Okay? So if you try to plug this in mathematically, your answer is 0. So what this is indicating is that there's no energy being transferred when ice melts. So if we follow the original Q equation, that's what it would tell us. However, these results make no sense. So the heat transfer during a phase change is going to need a different calculation. So we do know that there is energy to allow this to melt or freeze. That's not 0. It's 0 because we accounted for no temperature change. So we can't use the same Q equation. Okay, So here is the equation that you will need, and then we'll try some examples. So you can see it looks a little bit different. So instead of Q for TH, it's QPH for a phase change. And you don't have to write the pH every time. As long as you know how to solve this, you're in good shape. So if you notice now, it equals M for either one of these. M is mass. And then right here, heat of fusion or heat of vaporization. And where are those values going to come from? So if you remember, I gave you this chart, right? This is like specific heat. These are set values that I will provide to you. Okay, so this is the new equation for today. And then I'm going to stop this now and then put up a separate lesson to help you just with the math.